Alright, we're going to start with reviewing some basic trigonometry. Okay, so we're going to talk about a right triangle, the right triangle ABC, whose right angle is at B. We're going to look at the sine, cosine relationships. The sine of angle A, sine is opposite over hypotenuse. Remember SOHCAHTOA, sine opposite over hypotenuse, cosine adjacent over hypotenuse. Okay, tangent opposite over adjacent. So relative to angle A, the sine is A over B. Relative to angle C, the cosine is adjacent over hypotenuse, which is A over B. The cosine of angle A is the adjacent over hypotenuse, C over B, and the sine of angle C is the opposite over hypotenuse, C over B. So we see here that the sine of A is the same as the cosine of C. The cosine of A is the same as the sine of A. So we make a conclusion that the sine of an angle is the cosine of its complement. The sine of an angle is the cosine of its complement. Okay, and that's what this statement right here is saying, which is going to be known as an identity. Okay, the tangent of angle A, tangent is opposite over adjacent, so that's A over C. We now have some reciprocal relationships. We have 1 over the sine of A is the cosecant. The cosecant is 1 over the sine. So since the sine is the opposite over hypotenuse, the cosecant is the hypotenuse over the opposite. We have the secant of angle A. The secant is 1 over the cosine. Since the cosine is adjacent over hypotenuse, then the secant would be the hypotenuse over the adjacent. Okay, so the secant relative to A, angle A, would be side B, hypotenuse over C. The cotangent is 1 over the tangent, whereas the tangent is the opposite over the adjacent. The cotangent would be the adjacent over the opposite. Okay, we find similar relationships here. The cosecant of an angle is the secant of its complement. Okay, that's stated right here. Cosecant of an angle is the secant of its complement. The cotangent of an angle is the tangent of its opposite. Okay, we're going to take a pause here for a minute. Okay, we're back, and now we're going to start talking about our special right triangles, which we should know are the 45, 45, 90, the 30, 60, 90. Okay? Everybody knows that the Pythagorean theorem, one side squared plus the other side squared is equal to the hypotenuse squared for any right triangle. If we look at our 45, 45, 90 right triangle, and we assume that the side is 1, that the hypotenuse is 1, that is, then the other two sides are unknown, but they are also equal. So we'll say that A and B are equal, so they're both equal to A. So then our statement would come down to read A squared plus A squared equals C squared, but C squared is 1, so therefore we end up saying 2A squared is 1, so then the sides would be radical 1/2, which when rationalized would become, okay, 1 over root 2 times root 2 over 2, which is root 2 over 2. So in any 45, 45, 90, we know that the sides are root 2 over 2, and the hypotenuse is, okay, 1. All right, or and now from that we can find our relationships for the sine of 45. The sine of 45, and soon we will refer to radian measures in which we will say the sine of pi over 4, but for now we'll just keep it as the sine of 45 is, as the sine always is, the opposite over the hypotenuse being 1, so it's root 2 over 2. Cosine is likewise the same. Cosine, as we said previously, was again the sine of the complement, but the complement of 45 is 45, so the cosine of 45 is the same as the sine of 45, which is root 2 over 2. The tangent of 45 is the opposite over adjacent, which is root 2 over root 2, which is 1. Okay, I'm going to pause here for a minute again while we think about that. Okay, and we're back, and we're going to resume again now with the discussion of the 30, 60, 90 triangle. So in the 30, 60, 90 triangle, I think you'll recall 30, 60, 90 is basically derived from the equilateral triangle. So we took an equilateral triangle whose sides were 1, and we cut it in half. We would have a 30, 60, 90. And the side opposite the 30 would be half the hypotenuse, and then the side opposite the 60 would be 1/2 the hypotenuse times the root of 3. So the relationship here is 1, 1/2, and root 3 over 2. So looking at the sine of 30 degrees, which we will soon call the sine of pi over 6, but for now we just refer to it, that will be radian mode. Sine of 30 is 1/2, okay, because sine is the opposite over the hypotenuse, 1/2 over 1, which is 1/2, which would also be the cosine of pi over 3, or the cosine of 60 degrees. The cosine of 60 degrees is, okay, root pi, the cosine of 60 degrees, cosine is root 3 over 2 over 1, okay? The tangent of 30 degrees, the tangent of 30 is the tangent being the opposite over the adjacent, so the opposite would be root 3 over 1/2 over root 3 over 2, which becomes root 3 over 3, and the tangent of 60 would end up being root 3. Okay, so there is a table that illustrates that. You should know this table. Okay, the sine of 30 degrees. We're going to first come and give you those radian values. Don't worry about them right now. The sine of 30 degrees, you should know, is 1/2. The sine of 45 should be root 2 over 2. The sine of 60 should be root 3 over 2. Now, if you know these, you'll pretty much know everything else, because remember what we said earlier. The cosine of an angle is the sine of its complement. So the cosine of 30 is the sine of 60, which is root 3 over 2. The cosine of 45 is the sine of 45. And the cosine of 60 is the sine of 30, which is 1/2. Okay. The tangent of 30 is root 3 over 3. The tangent of 45 is 1. And the tangent of 60 is root 3. You really want to know this table and memorize this table backwards and forwards, okay? Every which way. sine, cosine, and tangent for 30, 45, and 60. Progression is, okay, 1, 2, 3. It's 1 over 2, root 2 over 2, and root 3 over 2. So root 1 over 2, which of course is 1, root 1 over 2, root 2 over 2, root 3 over 2. In reverse, root 3 over 2, root 2 over 2, 1/2. And, okay, the sine, we'll learn soon that the tangent is the sine over the cosine. So that would be root 3 over 3. Anything over itself is 1, and root 3. So you got to know these 9 values at all times, okay? So we'll stop this video right here, okay, and let you digest that.